Reactions involving alcohols. We'll start by looking at the preparation of alcohols. And a way to prepare an alcohol is by the hydration of an alkene. And this is a reaction that we saw earlier when we learned about Markovnikov addition of water across an alkene. And it says here, addition of water to the carbon-carbon double bond of the alkene produces an alcohol. And of course, this requires a trace of acid as a catalyst. And I told you that H plus just represents the acid catalyst because what's the definition of an acid? It's something that liberates protons. And so this H plus could mean sulfuric acid or phosphoric acid or simply hydronium. But what's happening here is that we're breaking the pi bond, right? The weaker bond here. We're breaking that pi bond and we're forming a bond, a new sigma bond between one of the carbons and the hydrogen from water, okay? And then we're also forming a new sigma bond between the other carbon and the hydroxyl to produce an alcohol. And of course, if you were looking at an unsymmetrical alkene, you would have to be able to identify both the Markovnikov and anti-Markovnikov products that we saw in chapter 11. Earlier on, we looked at the hydrogenation of an alkene to produce an alkane, but here we're going to look at the hydrogenation of an aldehyde or a ketone to produce an alcohol. And it says here that addition of hydrogen to the carbon-oxygen double bond of an aldehyde or a ketone produces an alcohol. And you'll remember that that carbon-oxygen double bond, we have a name for that. We call it a carbonyl. So when you add hydrogen across that carbonyl, you end up breaking one of the bonds and you form a new sigma bond between oxygen and a hydrogen. Now that sigma bond isn't shown, but it's the sigma bond that would be between this oxygen and this hydrogen. So that's one new bond that you form. And then you form another sigma bond or single bond between carbon and the hydrogen, which is this one here. You can see that the two R groups remain unchanged. You see the same R groups over here, they remain unchanged. Now, not only is this considered an addition reaction because we're adding hydrogen to the molecule, it's also considered a reduction because in organic chemistry, when we add hydrogen atoms to an organic molecule, we call that a reduction. So adding hydrogens equals a reduction. And just like the hydrogenations that we saw for alkenes that require a catalyst, the same thing applies here. When we perform a reduction on an aldehyde or a ketone to produce an alcohol, we also require a catalyst. And again, the same catalysts that were used with alkenes can be used, namely platinum, palladium, or nickel. I'll just add one more detail here. If you had an aldehyde, so let's imagine this R2, let's imagine this was a hydrogen. In that case, when you perform the reduction, you would end up with a primary alcohol. However, if that R group was an alkyl group, in that case, you would end up with a secondary alcohol. And so to summarize, an aldehyde undergoes reduction to produce a primary alcohol, and a ketone undergoes the exact same type of hydrogenation or reduction to produce a secondary alcohol. Now, we just spent all this time talking about how you can add water to an alkene to produce an alcohol. But what's interesting is that if you treat an alcohol with not only an acid catalyst but heat as well, you end up reversing that reaction and you produce an alkene plus water. So this is a dehydration reaction, right? The addition of water to an alkene to produce an alcohol was hydration. When we take an alcohol and again treat it with an acid catalyst, but we heat it, and that's the key. The key is the heat right here. When we heat that up, we can drive water out of the molecule to produce an alkene, and of course, we get water. We call this an elimination reaction because we're eliminating water from the molecule. And yes, it is essentially a reversal of the hydration reaction that we saw that formed alcohols from alkenes. Now, depending on the alkene, some alcohol dehydration reactions will produce a mixture of products. And the way that we predict what the major product would be is to use what's called Zaitsev's rule. And Zaitsev's rule states that in an elimination reaction, the alkene with the greatest number of alkyl groups on the double bonded carbon is going to be the major product of the reaction. So let's look at these two dehydration reactions shown down here. They're both the dehydration of 2-butanol. So the starting material is the exact same in both cases, and in both cases we're treating 2-butanol with acid and heat, but we get two different products. We get 2-butene, which is the major product, and we get 1-butene, which is the minor product. How do we determine which one is the major and which one is the minor product? Well, in order to affect the elimination or the removal of water, we're going to have to remove a hydroxyl, the OH, and we're going to have to remove a hydrogen. And to determine which hydrogens can be removed, you look at the carbonyl carbon and then you look at the carbons next to it. Now in the example on the top, they're looking at the carbon next to it and they're saying, okay, I'm going to pull the hydrogen from here, and then they make the alkene or the double bond between the two carbons I have highlighted in blue. For the example on the bottom, they did the same thing. They look at the carbonyl carbon right here, and we're going to have to lose the hydroxyl to form water. And we're also going to have to remove a proton. Now the proton they took off in this case was one of these three protons here. So again, you look at the carbons next door. In the top, they looked at the carbon on the left, but in the bottom example, they're going from the carbon on the right and they're removing one of these three hydrogens, because now you see what was once a CH3, a methyl, is becoming a CH2. And so they drew the double bond in 1-butene between the two carbons I have highlighted in red over here. Now we examine the products. If I look at the carbons involved in the double bond in 2-butene, you can see that overall there are two alkyl groups attached to both of those carbons, right? There's a methyl group on each one, and they both have a proton. So that's a total of two alkyl groups. When I look at the carbons involved in the double bond in 1-butene, you can see that I have 1, 2, 3 hydrogens and only one alkyl group. So one alkyl group. And what was Zaitsev's rule? Zaitsev's rule stated that the alkene with the greatest number of alkyl groups on the double bonded carbon is the major product of the reaction. So since this product has two alkyl groups total on the carbon-carbon double bond right here, it is going to be the major product. Sometimes we call the major product the Zaitsev product. Let's take a look at another example to help us get the hang of it. It says here, what are the major and minor products when 3-methyl-2-butanol is dehydrated? Well, again, Zaitsev's rule states that in an elimination reaction, the alkene with the greatest number of alkyl groups on the double bonded carbon is the major product of the reaction. So here we have the carbonyl carbon, I'll highlight it in blue. If you look at the major product on the top, okay, you go to the neighboring carbon. So let's start with the one on the left here. I have to remove the OH for my water molecule, and I need a hydrogen as well because water is made from H2O. So if I remove this hydrogen that I'm circling in blue, I would draw the double bond in between these two carbons that I have highlighted in blue, and I would end up with this product, 2-methyl-2-butene. If I go to the other carbon, so again, let me highlight my carbon. This time I'll do it in red, my carbonyl carbon. I need my hydroxyl for water. And if I was to remove one of these three hydrogens here, remember, you can go to the carbon next door. You can't go to any other carbons. So then, in this product, I drew the double bond between the two carbons that I have highlighted in red. And of course, I removed the hydroxyl and one proton to make a methyl group convert into the CH2 here. And I end up with 3-methyl-1-butene. Now let's examine the products. So if I look at the two carbons involved in the double bond in 2-methyl-2-butene, you can see I have a total of 1, 2, 3 alkyl groups attached to that double bond. And if I look at 3-methyl-1-butene, you can see I only have one, this isopropyl group over here, if you will, attached to that double bond. So since 2-methyl-2-butene has a total of 3 alkyl groups, and 3-methyl-1-butene only has 1 alkyl group. 2-methyl-2-butene is the more substituted alkene and is going to be the major product. Alcohols may be oxidized with a variety of oxidizing agents to aldehydes, ketones, and carboxylic acids. The most commonly used oxidizing agents are solutions of basic potassium permanganate and chromic acid. We represent basic potassium permanganate like so. And this is the molecular formula for chromic acid. The symbol O over the reaction arrow is used throughout this course to designate any general oxidizing agent. In order for oxidation of an alcohol to occur, the carbonyl carbon has to have at least one hydrogen attached to it. Now, a primary alcohol has 2 hydrogens attached to the carbonyl carbon, so it can be oxidized. And when a primary alcohol is oxidized, it forms an aldehyde as seen in the general equation, highlighted in green. And so if you are faced with a question like this, that says write an equation showing the oxidation of 2,2-dimethylpropanol to produce 2,2-dimethylpropanal. When you see the suffix al, this means you're making an aldehyde. So you can see that 2,2-dimethylpropanol is what kind of alcohol? It's a primary alcohol because the carbonyl carbon only has 1 carbon attached directly to it. And in order for the oxidation to occur, I have to remove 2 hydrogens, and then I form a double bond between the carbon and the oxygen of the alcohol to produce a carbonyl group and ultimately an aldehyde. Water should also be drawn to show the balanced equation. Secondary alcohols are oxidized to produce ketones. This reaction also involves the elimination or the loss of 2 hydrogen atoms. So you can see that we end up losing this hydrogen atom and this hydrogen atom. Remember what I said, that the carbonyl carbon has to have at least 1 hydrogen attached in order for oxidation of an alcohol to occur. So when we take our secondary alcohol, we end up with a ketone, and again, we draw water as a product to show the balanced equation. Tertiary alcohols do not undergo oxidation reactions under any circumstances, and the reason why is because there is no hydrogen attached directly to the carbonyl carbon. And so for the product of this reaction, you would simply write no reaction.